d theta 1 bar by dt. So d theta 1 bar by dt is equal to minus theta dot into r1 bar. So this is equation 4. Now where r dot is dr by dt and theta dot is d theta by dt. So now therefore the velocity v becomes dr by dt into r1 bar plus r into d theta by dt into theta 1 bar. So this equation we already derived in the last class. So this is the first dr by dt is nothing but the radial velocity, and d theta by dt is r into d theta by dt is the transverse velocity. Okay, so now to obtain radial acceleration and transverse acceleration, so now we differentiate this velocity term with respect to t. Why? Because acceleration is the rate of change of velocity. So therefore differentiating this velocity v with respect to t. So velocity v, and again this equation can also be written in this form, in the simplified form. So where dr by dt is r dot and d theta by dt is theta dot. So using these notations we write the velocity as this one. So r dot into r1 bar and r theta dot into theta 1 bar. Okay, so this equation and this equation both are same. Okay, so only we have denoted dr by dt as r dot and d theta by dt as theta dot, and we have written this equation. Okay, so both are one and same. So now this velocity v, this is the velocity term. Now to get acceleration term, we differentiate this velocity v with respect to t. Okay, so when we differentiate this with respect to t, dv by dt, so which gives the acceleration term a. Okay, a, which is equal to, now what we do here, we apply product rule for this term. So to apply product rule, what we do, keep first term as it is. Okay, that is r1 bar, differentiate r dot. So when we differentiate r dot with respect to t, it gives r double dot. Okay, so that is r double dot, first term as it is, differentiate second term, that is r double dot, plus second term as it is, r dot, differentiate the first term, that is r1 bar dot. Similarly apply product rule for this term, and we get this equation, So now what we do, we substitute r1 bar dot and theta 1 bar dot from equation 2 and 4. Now see, this is what we I told we need extra quantities. Okay, so that is r1 bar dot and theta 1 bar dot. So r1 bar dot is nothing but theta 1 bar into theta dot, and theta 1 bar dot is nothing but minus theta dot into r1 bar. Okay, so now what I do, I substitute r1 bar dot, so here, and theta 1 bar dot. Okay, from those equations, r1 bar dot and theta 1 bar dot. Okay, so now I replace those terms. So acceleration becomes r double dot r1 bar as it is, r dot into r1 bar dot is nothing but theta 1 bar into theta dot. Similarly r dot into theta dot into, this is theta 1 bar, then plus r theta double dot into theta 1 bar, this is correct, and here r theta dot, and here it is theta 1 dot bar it is, and this I will replace by minus theta dot into r1 bar. So substituting r1 bar dot and theta 1 bar dot from 2 and 4. So here one is r1 bar dot is here, and theta 1 bar dot it is here. Okay, so from 2 and 4 we substitute r1 bar dot and r theta 1 bar dot in this equation, and I'll get this equation. Okay, so therefore a is equal to, now in this case take r1 bar common, wherever r1 bar is there, take r1 bar common. Now see here, in the first term r1 bar is there, and then and one more term in this term where it is r1 bar into r theta dot square. Now see here, okay, in this term r1 bar is there. Okay, so after multiplying these two products, so it becomes r dot, sorry, r theta dot square into r1 bar with negative sign. This is minus r theta dot square into r1 bar. So here r1 bar and here also it is r1 bar. So from these two terms, take r1 bar common, and in bracket we left with r dot, r double dot, then here minus. So we have taken r1 bar common, and here we left with r into theta dot square, r into theta dot square. Similarly, plus, take theta 1 bar common. So now theta 1 bar is here and one more theta 1 bar is here. So in these two terms, sorry, in these three terms, theta 1 bar is common. Take theta 1 bar common. So now we will get r dot theta dot. Okay, then here also when you take theta 1 bar common, r dot theta dot. So this r dot theta dot and this r dot theta dot gives 2 r dot theta dot, and here theta 1 bar I will take common, and r into theta double dot is left. So this is expression for acceleration. Now here the coefficient of r1 bar, it is called as, this term is called as radial acceleration, and this term, that is coefficient of theta 1 bar, so that is this term is called as transverse acceleration. So that is radial acceleration is equal to r double dot minus r theta dot square, and transverse acceleration is equal to r theta double dot plus 2 r dot theta dot. Okay, so now we solve some problems. So the problem one is, it is the problem, the velocities of a particle along and perpendicular to the radius from a fixed origin are lambda r and mu theta, where lambda and mu are constants. Show that accelerations along and perpendicular to the radius vector are lambda square r minus mu square theta square by r and mu theta into lambda plus mu by r. Find also the equation of the path of the particle. So this is the problem. Now in this case, what is given? The velocities of a particle along and perpendicular to the radius from a fixed origin means that radial velocity and transverse velocities are given. So radial velocity is lambda r and transverse velocity is mu theta. Okay, so now what we have to show, accelerations along and perpendicular to the radius vector. So acceleration along and perpendicular radius vector means these are radial acceleration and transverse acceleration. So we have to prove radial acceleration is equal to this term and transverse acceleration is equal to this term. Okay, and it is also given, it is also asked to find equation of path of the particle. Okay, so this is the problem. Now first write the given equation. Radial velocity is equal to dr by dt, which is given as lambda r. Call this equation as